Welcome everybody to the session moving on to looking at the application of Cyclone to existing code, and so to the NEMO API of Cyclone. So I'll just give you a brief overview of what we're going to do today. So we have an hour and a half today where I'm going to kick off by giving you an overview of NEMO in case you're not familiar with it, its performance characteristics, and then looking at how Cyclone deals with this existing code. And then I'll talk a little bit about the mini app that we're going to use in the hands-on sessions. And then following on from that, we're going to a hands-on session where you really just start playing with applying Cyclone to the existing Fortran code in the mini app, just investigating the CIR that it produces and things like that. And then once you've done that, we'll have another little bit of a presentation where I'll talk through some of the transformations that are used within the NEMO API. And then after that, there'll be a bigger, longer hands-on session where you can start playing with those transformations and use them to add profiling to the mini app. And that will be today, and tomorrow we'll move on to looking at OpenMP and Openhack, but that's for tomorrow. So let me find my other presentation. No, that's not going to do it. Here we are. Right, hopefully you can see that. So as I said, this is an overview of using Cyclone with the NEMO ocean model. Oh, and I've got fancy things in it. I didn't know I got those. Right, so this is an outline of what I'm going to say. I'm going to give an overview of the NEMO ocean model first, because obviously not all of you will be familiar with it. And in particular, its coding conventions that it follows and the performance characteristics that it has. And then I'll move on to talking about how that makes it suitable for using something like Cyclone in order to transform it. And then I'll talk a little bit about how that works, because up until now, we've obviously mostly focused on the ELFRIC API, which is code written to the Cycal separation of concern, so that, and Cyclone generates code for that, whereas now we're looking at code that pre-exists. So it's a bit of a change in mindset. And then I'll say a little bit about the mini app that we're going to use in the hands-on sessions. So the NEMO ocean model is a finite difference model, uses a tripolar, strictly a latitude-longitude mesh, except they've done clever things to it. So it's stretched, it has 3 poles, and that means that they can put the poles over the land so that they don't have the same problems of going to high resolution as the atmosphere model does, because the points, those, I can get a pointer, can't I? Or maybe I can't. Can you see my cursor, Rupert?
Yes, we can.
Great. So the poles you can see here where the resolution of the mesh goes very high or over land, and obviously you're not worried about what happens on land. You can mask that out. So unlike in the atmosphere where there was a real need to rewrite and change the way the meshing is done, and therefore the way the science is done, in the ocean world it's not quite as pressing, and therefore there's no great push to change it. And that's why we're dealing with existing code and not looking at a new model. NEMO itself consists of 3 core components. There's the ocean dynamics and the thermodynamics. There's the sea ice cube SI3 model that does the sea ice. It's quite a computationally expensive part of the model, but obviously you only have sea ice at the pole, so there's a load balance problem there as well. And then there are other components that deal with tracer transport, so biogeochemical models, that kind of thing. And as with codes in this domain, it's pretty large. It's about the core of it, those 3 bits are about 100,000 lines of Fortran. And then there are other modules that, depending on what configuration and what science you're doing, you might or might not compile into your executable. NEMO has, one of the reasons we're interested in it is it has a large user base. It's used by the Met Office, it's used by ECMWF, it's used by Surfax, it's used by a whole range of people around in Europe and around the world as well. It's a trusted part of the climate model intercomparison project, and it's constantly under scientific development. So it's not as though you can go away, optimize it, spend 6 months optimizing it, and then come back and expect everybody to be happy about that, because while you've been doing those optimizations, they will have been changing the source code and adding new science to it. Those developers are typically oceanographers. They're not computer scientists or computational scientists. NEMO itself has a long history. It's of the order of 20 years old, and it's still going. And if you think back to what supercomputers looked like 20 years ago, it was a very different world, and you would make different decisions then that you would make now if you were starting a new code. And as Rupert talked about in his talk on the 3Ps, there's always trade-offs, and you have to decide what it is you're going to focus on. And in NEMO, they have chosen to focus on scientific correctness, on maintainability, which in some ways maps to productivity, because you've got to have code that the developers who are oceanographers are confident and comfortable working with. There's no point trying to give them something that they don't like, because they won't use it. And it's got to be portable. I mean, it's, as I say, this code has been going for 20 odd years, and obviously it has to be able to move and be run on whatever supercomputer you have access to now. But that has brought some problems, because in their focus on making sure that the code is understandable and maintainable, the developers have chosen not to put directives in of any sort. So there's no OpenMP and there's no Openhack in there, which means that currently NEMO can only run on CPU, and it can run in serial or it can run MPI parallel. As with many codes of this type in this domain, it has what we call a flat performance profile. So that means that when you profile the code and measure how much time is spent in each routine, you find that no one routine accounts for very much time. So in this is just a quick plot I put together to make my graph, my slide look a little less boring. You can see that, well, you can't quite see, but no one routine accounts for more than 10% of this run. And if I was to scale it out and run on more cores, then that would get flatter. And then you have this typically long tail where there are lots and lots of routines that take, just a few percent, but there are a lot of them. NEMO itself is dominated by stencil operations, and they are typically memory bandwidth bound. You're reading from a lot of arrays and maybe only writing to one array. So it really depends on how fast you can get all of that data out of memory in order to operate on it. NEMO has a functionality to exclude any subdomains that only have land points in them. So it's not really worth going into the details of that. But if you imagine you tell it how you want it to decompose the domain, and it does that, and then it examines the subdomains, and if there are any that only consist of land, then it doesn't bother simulating those. As a result, it has pretty good MPI strong scaling performance. But as I noted on the previous slide, it can't make use of GPUs. And obviously, if you look at the top 500 or the top 10 of the top 500, that's getting to be a bit of a problem, because most of the big machines, much of the compute power on them is made up of GPUs. Some people have taken matters into their own hands a bit. So ECMWF, because of the way they couple NEMO with their atmosphere model, they have had to add OpenMP themselves, and they've taken on then that maintenance burden of keeping an OpenMP version of a code base that doesn't have OpenMP in it by default. So it's a large code base, and it has a flat performance profile, so you can't just optimize a couple of routines and be done. But there are things about NEMO that make it amenable to applying a domain-specific language to it. So one of those is the fact that the code base is fairly homogeneous. It's mostly stencils. You look throughout the code, and it's mostly doing loops over grid points and doing some stencil operations on them. Second to that is the fact that they have very strict coding standards. So for instance, if you look at the code on the left here, I know a NEMO developer would know that a loop over JK is a loop over vertical levels, and JPK is the number of vertical levels in the model. And there are various other things like that are enshrined in a document, and that's what the code has to conform to. And then, because we know it's an ocean model, we then have domain-specific knowledge. So as I said, I know that JK loop is a loop over vertical levels. I could even go down as far as to say that, typically I know that that's of the order of 100, and therefore there might be choices to make there about how you parallelize things. I know that the I and J loops are longitude and latitude. I know that there are also tracer species in this thing, so temperature, salinity. If you're doing biogeochemistry, then there's all sorts of other tracer species that come in. I could go further. I could say I know that something beginning ln underscore is a constant that's been read in from a name list, so it's constant over the duration of the run. Therefore, if I encounter some if statement with it in, then I can reason about that. And then also I know about temporary variables. So the coding convention is, for instance, that there's this z slope x and z slope y. I know because they begin with z, they're temporary arrays. They're only used within this particular subroutine, and then they're thrown away again afterwards. So there's a lot of domain-specific knowledge available to us. So in terms of front ends, or domain-specific languages, rather, I should say, we have there's a sort of continuum going from the left, where you have completely unmodified existing code. So, and that's where we are now. It supports evolution. It's where the scientists are and where they're happy. But it has performance limitations. So, for instance, for NEMO, that means you can't run on GPU, for instance. And then you could go all the way over to the right, where your model is entirely specified in a high-level domain-specific language, which means because you are so tightly controlling everything, you can get very high performance out of it, and that's great. But it requires a rewrite because you have to rewrite your whole code in this domain-specific language. So in terms of the two models that we've looked at so far from a Cyclone point of view, we have Elfric and we have NEMO. Elfric has chosen a middle way, I think, in a way, in that some of it is a high-level DSL, and the algorithm, for instance, is quite a high-level DSL, but then the users are still implementing the kernels themselves, or at least the ones that aren't built-in are still implemented themselves, and they conform to a certain data model. So it is revolution, but it isn't all the way over on the right-hand side. So we're sticking with Fortran, for instance, so that brings the scientists along with us, but there are some compromises that have been made in order to do that. NEMO, on the other hand, is obviously over on the left-hand side. It is unconstrained. The scientists can pretty much do what they like. It supports evolution because that's where they are now. And it has performance limitations. So obviously although I've just described some of the domain-specific knowledge we have about NEMO, there are limits to that, and we haven't got as much information as we would have if we were over here and had said the users had to rewrite everything in a high-level language. So it's a choice that we make. So our strategy, where this work came from, was originally we thought, sort of coming off the back of Elfric, we thought, oh, this is great. The Cycal separation of concerns is really nice. It makes code more readable. And so we showed this to the NEMO consortium, and the NEMO consortium weren't convinced. They didn't want to rewrite code. They liked their code the way it is. So, and at the same time as that, Nvidia had experimented with applying Openhack directives to NEMO, and Jeremy Appleyard had done that for I think the Gyre configuration of NEMO, so sort of the ocean-only benchmark configuration of NEMO, and he'd got good performance on GPUs, primarily just using these Openhack kernels directives. So really just getting the compiler to do its thing and giving it a bit of a hand along the way. But as I mentioned earlier, you can take a branch, you can go off and do that, and that's fine. But while you're doing that, the trunk of NEMO moves on, and it moves on fast. And so that branch, although it showed good performance, because it involved directives that the oceanographers aren't comfortable with, and because it was, forked off at some point, it's been left behind. So it's a good demonstrator, but it's only a demonstrator. So the idea that we wanted to take forward was to use Cyclone to replicate what Jeremy had done, but obviously to do it automatically without any manual modifications. And once you have the power of being able to do it automatically, then ideally you can do it to any NEMO configuration, so no matter what particular science modules you're using. As part of that, we use Nvidia's managed memory option to deal with data movement between the CPU and GPU. Initially, we thought this would just be a quick way to get us up and running while letting the underlying subsystem worry about where the data lived. But actually, it's proved really quite successful, and particularly once you get to complicated data structures, it's really the only manageable way to go. So increasingly, we're relying on Nvidia's managed memory technology, which basically uses page fault. So if the code on the GPU comes to access some memory and it's not available on the GPU, then it automatically gets pulled across to the GPU, and vice versa. It gets pulled back to the CPU if necessary. I'll talk a bit more about that in the hands-on exercises. And finally, we've extended Cyclone with functionality to introduce more tailored Openhack directives. So although we primarily rely on adding Openhack kernels into the code, there are cases, and you'll see these in the hands-on, where we know, for instance, because we know the rough dimensions of the loops that we're dealing with, we know about the number of vertical levels, and we know about the extent of the latitude and longitude. We know we can give the compiler hints essentially as to what it should do, and so we can get a bit more performance out by doing that. So this is a slightly shinier version of the picture that you've seen already, highlighting what I'm talking about now, which is the route through for NEMO. So in NEMO, we start off obviously with existing Fortran code on the left here. That comes in, is parsed by fparser, not shown here, and then our NEMO front end in Cyclone then takes the parse tree produced by fparser and constructs the Cyclone internal representation of the code. And then, as you've been playing with in Elfric, you apply transformations to the SciIR just as you do in Elfric. And then once you've transformed the SciIR, the resulting code is written out back to Fortran again. In principle, we can go other ways. We could, in principle, generate OpenCL, and we can, in a limited sense, generate intermediate representation for the Dawn tool that Carlos et al. Will be talking about in the second half of this week. But for now, I'm going to concentrate on generating Fortran out at the end. One of the key things that you need to be able to do when you're applying Cyclone to NEMO is to understand the way in which the Cyclone internal representation is constructed, because it's that you're going to target with transformations, and therefore you need to be able to understand what it is you're looking at. So I'm just going to go through a few examples here to help you get to grips with it, so that when it comes to the hands-on bits, you'll know what you're doing. And if you get stuck, of course, in the hands-on, then we'll be available on Slack to help. So a key part of the NEMO coding convention is the use of Fortran array notation, which, in case you're not familiar with Fortran, is the use of colons here. So this, for instance, is effectively an implicit loop saying set all the values of this ZWY array at vertical level JPK to be 0. So basically you're setting the top of these two arrays, if you like, to 0. And that's an implicit loop. So in the SciIR, that becomes an assignment. You're assigning ZWY to 0, obviously, except that ZWY is an array reference. And you know more than that. You know that, in fact, it's an array range. So underneath array reference, you see you have a child for each index in the array. And the first child is a range because you've got a colon there, so it's a full range. The second child is a range because you've got another colon there, and then the third child is just a reference to the JPK symbol, which is that element there. So that rather verbose bit of SciIR is describing this array assignment here. So that's the first thing that you need to know. More straightforward are the explicit loops, of which there are also a lot in NEMO. And you'll have seen these and be fairly familiar with these from the Elfric examples. Obviously in NEMO, it's slightly different. So instead of loops over cells and over DOFs and over colors, we have loops that we recognize as being over latitude or over longitude, or off the top of my little picture here is levels. So you've got a levels, latitude, longitude, triply nested loop. And then inside, you have what we call an inlined kernel. So if this was a code that followed the Cyclone separation of concerns, then obviously these two lines here, this calculation of ZWX and ZWY, would actually be done in a separate kernel. But NEMO doesn't follow the Cyclone separation of concerns. So you can think of this conceptually as somebody having taken the contents of a kernel that computed those two things and manually inlined it inside this loop nest. So in the SciIR, we think of that as being an inlined kernel. And then underneath the inline kernel, you have the SciIR of the kernel, if you like. So you can see, again, you've got an array reference, and it's being assigned the result of a multiplication, and so on, down the SciIR. So the key things to take from here are you still have loop nodes. The loop nodes have types, so you can identify what type of loop you're looking at. And then inside those loops, if it is something that Cyclone recognizes as doing computation, then you have an inlined kernel. Another crucial part of the SciIR that's very important when it comes to looking at existing code like NEMO is this code block concept that Sergi talked a bit about in his talk on the SciIR. And the code block, as a reminder, or to tell you if you didn't make Sergi's talk, is a bag in which Cyclone puts anything it doesn't understand. So it's very powerful because it means we can parse code and manipulate code even if we don't fully understand all of the code that we're getting. But it does then present a barrier to us if we want to optimize. So in this particular simple case, for instance, you can see that in the middle of this loop, there's a write statement. Maybe it's writing to file or something. In fact, it is in this case, it's writing data to a file. And we haven't bothered to implement support for the write statement in the SciIR because write is not something that involves any computation, and SciIR is all about representing computation. And therefore that statement there ends up in a code block. So you can see the code block down here, and you can see in the text representation of the code block, it gives you a hint as to what it is that's in it. So you can see that this is a write statement that fparser has identified. And if there was more than one statement there, you'd have a list of them in here. And because this loop contains a code block, you'll see that it doesn't contain an inlined kernel because a kernel can't do I/O. So, or if there's any statement that Cyclone doesn't understand, so if you end up with a code block, then you cannot have a code block inside a kernel. So there's no kernel here. It's just a triply nested loop with a code block inside it. And that can be important when it comes to applying transformations. You might want to, for instance, make sure you only apply transformations to kernels that contain loops. Other way around, to loops that contain kernels. So moving on now to think about the tracer advection mini-app. So all of the hands-on sessions, all of the NEMO hands-on sessions will use the tracer advection mini-app. It was originally developed by CMCC and kindly provided to us by Sylvia. It forms the basis of the NEMO dwarf, which you may have heard of, which has come out of the Escape project. And it's pretty much cut and paste of a tracer advection routine from NEMO, and it's always high in the performance profile. In fact, it was the #1 routine in the profile I showed you earlier. In the tracer advection mini-app version of this code, the outer loop that would normally be over tracer species in NEMO has become an iteration loop, so it's just a way of increasing the amount of work that is done. As I said, as I was talking about NEMO, this kind of stencil access that is performed in the mini-app is representative of the majority of NEMO. This particular routine has had the MPI removed from it, so there's no MPI in this benchmark. It consists of a few hundred lines of Fortran, and it doesn't need to read any data or anything. It just generates synthetic data for the purposes of running. It does output data at the end, I think, which we do use to check we haven't broken anything when we're parallelizing, but that's the only reason we use that. So that completes the first part of this presentation. The next step is to begin the hands-on session. It's possible, if you've got a lot of experience already from doing the earlier hands-on sessions, that you might find this first one a bit easy. But if that's so, then you can get an extra cup of coffee, that's fine. In case you haven't already, you will need to clone Cyclone and then install that cloned version of Cyclone. And then the tutorial, this first one, is under Tutorials, Practicals, NEMO 1. And if you go into there, there's a README, which, as with the other READMEs so far, renders nicely in a web browser if you go and find it. In fact, I've given the URL there. And then myself and Rupert and everyone will be available for questions on Slack. And I forget how long I said to allow you for this. Let me just check what I said. I think it's about 20 minutes. Yes, so 20 minutes. So I've gone a bit over, but I tell you what, we'll plan to come back at, I'll plan to come back at 3 o'clock, I think, and as long as everybody's done by then. So I shall see you on Slack, and that completes that first part. Thank you. Hello again. Hopefully that went okay for those of you that didn't have Python 2/3 problems. And hopefully you got to a point where you were able to run the mini app and investigate the SciIR that was created. If you didn't, then do feel free to ask questions on Slack. So now I'm going to move on to talking about transformations in a bit more detail. Some of this information or some of this detail is stuff you should already be familiar with if you've been to previous presentations about Elfric, but just in case you haven't, and in order to remind you, because it never hurts to be reminded, I'm going to talk through some of the transformations that we're going to use in the next stages of the hands-on practicals now. So I'm going to talk about single and region transformations, and then I'm going to talk about profiling, which is what you'll be doing in the next hands-on session, and then I'm going to talk a bit about OpenMP and Openhack, which is what we'll be doing tomorrow morning. And then probably the most important bit, I'll be pointing you to where you can find out more, because I'm hoping that as you work through the hands-on tutorials, you'll be able to look at the documentation and be able to work out the answers by looking at the documentation.
And Andy, so, are you showing slides at the moment because we can't see them?
You can't see? Oh, I'm not sharing my screen, am I? Duh. Hold on. Thanks, Rupert. It's a good job somebody's awake. Right, you see that?
Yes, thank you.
Great, thanks, Rupert. Okay, you haven't missed much. That was my overview. So single and region transformations, profiling, OpenMP, Openhack, and finding out more. So there are two basic types of transformation. As you might guess, the single node transformation acts on just one SciIR node, whereas a region transformation acts on a list of one or more SciIR nodes. That list of nodes, they must all be siblings. So for instance, in the schedule below, 0, 1, 2, 3, 4 are all siblings. So that would be fine. Excuse me. We try to have a slightly nicer API where if you're only supplying a single node, you don't need to make a list out of it. So these region transformations will work on a single node as well as a list of nodes. I say try because we discovered a bug where that wasn't always true, so there might still be bugs around, but that's what we're aiming for. And the helpful thing to remember is that when you're looking using the view method in the SciIR and you get out this kind of textual representation, the nodes that are candidates for being targeted with transformations are numbered. So if they're not numbered, then they're not a target for a transformation. So for instance, you can see just off the bottom here, this loop node has some children, but those immediate children are actually the bounds of the loop. So there's the lower bound and the upper bound. And obviously you can't target those with a transformation, or at least we don't have any transformations that target them yet. So they aren't relevant. So it's just the numbered ones. That's the important thing to remember there. Using a transformation, Jörg covered this quite well this morning, but in case you missed it, and to remind you, the most straightforward and reliable way of doing it at the moment is to import the Python class directly. So many of them are under transformations under the SciIR, and you can import them when you want. And then you need to create an instance of it because you've imported the class, so you create an instance of it, and then you apply it. Is the main thing you need to remember. You can optionally call validate first if you're doing a more sophisticated script and trying to work out how many nodes you can add to a single transformation before it breaks, for instance. You might want to use validate. If you don't validate, it doesn't matter because the apply method will always call validate for you anyway and check that everything is okay before it applies the transformation. If validate fails, it will raise a transformation error exception, which you can catch if you wish. So for instance, the profiling transformation, again, this is reiterating what Jörg said this morning, but this time we're now applying it to NEMO source code, which is much less well specified than the Elfric version. So the profiling transformation, you apply a single transformation on a list of nodes that you want to enclose within a profiling region. And then it automatically, at code generation time, inserts the start and the stop calls around that region of code. And those start and stop calls are actually calls into a wrapper library for the SciData API. And what library you actually call at execution time is determined purely by what you link to at compilation time. For profiling is pretty relaxed about what you can include within it, because you're not actually parallelizing any code. Obviously, you're just putting timers around it. So the only thing that is forbidden from being inside a profiling region is the return node, because obviously you don't want to start a timer and then have your code jump out of it with an early return. That would be bad. So return nodes are forbidden. Anything else is allowed. So even code blocks, for instance, are allowed. So in this example here, I've got a little fragment of the script up here that is simply enclosing all of the children of a schedule. So the whole invoke essentially is being enclosed within a profiling region. And in this case, that profiling region then includes some code blocks, which are, again, their write statements, as you can see from the fparser2 stuff here. And that's fine. They're okay to be within a profiling region. Now, because Cyclone, whether or not it's the Alfric API or the NEMO API, Cyclone doesn't know about the structure of your application. It doesn't know, if you like, where your main routine is. It doesn't know where the time stepping loop is. And therefore, it has no way of working out where to add any startup and any shutdown calls. So that has to be done manually by the user. And the hands-on example that you're about to do now will get you to do that. For the profiling library that you're going to use in the hands-on session is only actually the shutdown call that is required. It doesn't need a startup. It's very simple. But in more complicated and general cases, you might need to add a startup as well. And obviously, where you put that will depend on whether or not it understands about MPI and whether it needs to be done before or after MPI has been set up. So that is something that has to be done manually, but only once. Just to show you that this functionality is working and is useful, this is a profile. Well, it's a gratuitous picture really, but it's a profile from the work that we're doing porting NEMO to running on GPU, and it's using Nvidia's NVTX library. So there's an existing SciData wrapper library for NVTX, so that when you link, so you build your application, you link it with the necessary SciData wrapper library and link it against NVTX, and then all of those calls to the SciData API get mapped down into NVTX, and that means you can then label regions in the Nvidia Profiler, because certainly in the Visual Profiler, the older version of the Visual Profiler, if your code wasn't running on the GPU, then you got no information. You just had white space here. Like, in fact, you can see these gaps here, though. So that's the code is not running on the GPU, but you don't know what code it is. It gave you no information about that. So with this additional profiling information that Cyclone adds, you can follow it down the call stack, and you can see you're somewhere in the ICE model, and you could zoom in on this and it would show you which routine you were in. So it's very useful, because of course when you're automatically applying transformations to a code and it's a big code, you need tools to help you work out where it was you maybe didn't do the job you thought you were doing. So that's just an example to show that it's useful. For the OpenMP transformations, we're going to look at using 3 different transformations. Again, Rupert covered some of this actually. So, and they're named for the directives that they add. So if you're familiar with OpenMP, then hopefully the naming scheme is familiar. So an OpenMP loop transformation just adds an OpenMP do directive to a loop. So its target for that transformation must be a loop. If you don't give it a loop, it will reject it. And this comes back to a question actually that Will Sawyer asked on Slack. We don't mandate what order you apply transformations when you're transforming code. You can do what you like, but that does mean that we have to then do checks at code generation time to check that what we've been given is valid. So for instance, an OpenMP do directive, because it says execute this loop in parallel, you have to be within some parallel region, so it will check that at code generation time. OpenMP parallel loop trans, on the other hand, effectively is a combination of those 2 things for a single loop. So it says start a parallel region and make this loop parallel. And we'll do a bit of that because that's a very easy way of getting OpenMP into a code. And then the final one is OpenMP parallel trans, which just creates an OpenMP thread parallel region, but doesn't say how you want to share work between threads. That requires a subsequent OpenMP loop transformation. When you apply those transformations, you'll see if you're using the colored output of the SciIR, then you'll get green nodes appear, these directive nodes, and then it will give you a little bit of detail about what the directive is. So you can see you've got an OpenMP parallel region out here, and then that contains this loop over the vertical levels that has an OpenMP do applied to it. Openhack is very similar, as those of you who know it will expect. It has the same concepts of a loop and a parallel loop. Where it differs are, as Rupert again talked about, there's the kernels transformation, which we make a lot of use of in the NEMO API, because essentially we're just using the power of the compiler to do the right thing and look for parallelism and automatically offload any kernels it finds to the GPU. And then significantly different from the CPU targeting OpenMP, you have to worry about data movement with the GPU, as Rupert also talked a little bit about. And there are two different data related transformations in Cyclone, one of which we will use in the hands-on tutorial tomorrow and one of which we won't. The one we will use is data trans, which creates what's called a structured data region. So it has a static scope. When you enter it, data is copied over to the GPU. When you leave it, data is copied back from the GPU, but you can control that with clauses. And we'll use that for the simple walkthrough tomorrow that you're going to be doing tomorrow morning. Right, and with that, yes, where to find out more. So some of you hopefully have already found it or been pointed to it, but we endeavor to document everything as we go, as we develop. And so there's the user guide. The user guide has documentation on the various transformations that are available. So you can see here, you can look at OpenMP, there's Openhack, and then there's others available as well, but we won't be covering those in this tutorial, but you're welcome to have a look, of course. The only thing I would say, and I found out while writing this tutorial, is that they're not indexable, unfortunately. So I haven't been able to give you direct links to the precise transformation. But if you go in, open it up, and then search for the one you want, you will find it. So that's a useful resource. Possibly more useful because it's more easily searchable and it has everything in it, at least I find it useful, is the reference guide. So if you go to cyclone-ref and read the docs.io, you will be presented with two options. There's the Sphinx Auto API, the Sphinx Auto API generated version of the documentation, and there's the Doxygen generated version of the documentation. I find the Doxygen one to be a bit more useful. It's a bit more fully featured, and it lets you explore the classes, and you can find each class, and then, as I've shown here, it'll give you all the documentation. Whoops, no, that's not what I wanted to do. It will give you the documentation for the transformation, including an example of how to apply it, for instance. So that can be very useful in working out what you need to do. So with that, I will let you get on with the hands-on session. So the next hands-on session is going to be basically the idea is to get you used to applying transformations, although probably if you've done the earlier tutorials you might already be quite au fait with that, but if so, that's great. Hopefully they're slightly open-ended, so if you are very familiar and you get through it quite quickly, you can do a bit of exploring yourself. They are here, so tutorials, practicals, NEMO 2_NEMO_ profiling, and as usual, please bother me on Slack if it doesn't work. Thanks very much and have fun.